Hey, welcome back to your favorite Fundamentals College Math class. We're going to take a look at probability, specifically independent events initially. So the probability of A and B, if they are independent events, would be the probability of A times the probability of B. Okay. So let's do an example of that here. Suppose. And we should say, what is an independent event? And events are independent if the probability of event B occurring is the same whether or not event A occurs. So in other words, event A has no impact on event B. So for example, you flip a coin and roll a die. If you flip a coin, it does not change the probability of rolling the die. It has no impact on it. But if, let's say, you had a certain amount of marbles, 3 red, 2 blue, 5 green, the probability of picking one out, if I don't replace it and I pull another one out, event A impacts event B because I have a less amount in the bag when I pull the second one out. So that's a dependent event. That's different. Okay, so we'll have discussions surrounding that as well. But flipping a coin and rolling a die, these are independent events. So what's the probability of flipping a heads and rolling a 6? Well, if I use probability of A times probability of B, it'd be probability of the heads times the probability of the 6. Well, the probability of flipping a coin and getting the heads is 1 out of 2. Probability of taking a die and getting a 6 is there's one number 6 out of 6 possible outcomes. So then I just multiply the numerators. 1 times 1, 2 times 6. So the probability of flipping a coin, getting heads, and rolling a die and getting a 6, I have a 1 in 12 probability of that happening if I flip a coin and roll a die to get a heads and a 6. I have a 1 in 12. Now this scenario, you could probably visualize this by just writing out all the possible outcomes. You could flip a coin and get a heads and a number 1. You could flip a coin, get heads and a 2. You could flip a coin, get a heads and a number 3. Flip a coin, maybe you get number 4. Flip a coin, you get a heads and a 5. Flip a coin, get a 6, right? Now, what if you got a tails with a 1? A tails and a number 2. A tails and a 3. These are all the possible outcomes. Notice all those possible outcomes, what we wanted is we wanted to get a heads and a number 6. There's only one winner out of 12 possible outcomes. So this one you could visualize that, right? But we're wanting to practice using this formula up here. Probability of independent events. Probability of A and B is probability of A times probability of B. All right, so this one we've got this bag. We've got 3 red marbles. We got 4 blue. We got 5 green. Okay, part A says you randomly draw a marble from the bag. So we pull one out. And then we proceed to do a second one. Well, if I pull out a second one, I have one less the second time, right? This was our prior discussion. So it's going to, event A, I pulled one out, affects the probability when I go to grab another marble, because instead of having 12 in there, now I only have 11 out possible marbles to choose from on the second. Okay, so part A is a dependent. This is dependent. This is not independent. All right, because this is a without replacement. I did not put the marble back in, right? So I only have 11 marbles in there when I go to draw the second one. So event A affected event B. Now part B, second question on this says, you randomly draw a marble from the bag, but then you replace the marble. You put it back in. Well, if you put it back in, that's different. This is called with replacement. So I take a marble out. But I put it back in. Well, if I put it back in, it's just like when I started. So event A did not impact event B, because I still, when I go to pull the second time, I still have all 12 marbles in there. So this is with replacement. So these are independent events. Okay. How about these? Are these independent events? A fair coin is tossed 2 times. The first toss ahead, the second toss ahead. Are these independent events? Well, let's go ahead and just do it. If I flip a coin, does that impact the probability of flipping a coin again the second time? Has no impact, right? I still have a 1 in 2 chance. So these are independent events. Independent events. So like the probability of flipping a heads and a heads would be the probability of flipping a heads times probability of flipping a heads. So it'd be 1 out of 2 times 1 out of 2. Or 1 out of 4. All right. You know what? Before I do this card one, let me go back up here to this one for just a second. I kind of want to revisit this scenario. Let's do part B. Let's do probability of pulling a red and a blue. Since they're independent events, it'd be probability of red times the probability of pulling a blue. So probability of pulling a red out is 3 out of 12. Now I pulled, let me erase this for a minute. I pulled a red out. But remember, I'm putting it back in for part B. I'm putting it back in. So all 12 are still in there when I go to pull a blue one out. Now I want to pull a blue one out. So probability of pulling a blue one out, 4 out of, remember, all 12 are still in there, right? So it'd be 12 out of 144, or 1 out of 12 would be our probability, right? Now that's different than part A, because if I don't replace it, so let's do part A. So let's say I pull a red out. I want to pull a red out. Well, I'll do the same thing. I want to do a red and a blue, but I don't put it back. A red and then a blue. So probably this is without replacement. Probability of pulling a red and a blue. Well, to pull a red out, it's 3 out of 12. But remember, the red stays out. So when I go to pull a blue out, now I'm down to 2 red. So I'm down to 11 left. What's the probability of pulling a blue out? Well, how many blues do we have? 4. Yeah, so it looks like I'm, multiply that out. Looks like I'm 1 out of 11 there. Part B here, I'm coming back to this. We're drawing a card from the deck. Then we draw a second card without replacing. This is without replacement. So part B, I'm taking a card out. Let's say that, so the first card, I got all these cards, right? First card's red, but I don't put it back. Next card's red. So this is without replacement. Again, this is dependent. This is not independent events. This is different. But we might as well, we can go ahead and figure it out. Probability of pulling a red out and then another red. Probability of red and red. Well, probability of pulling a red out, how many reds do we have? 13 plus 13. Looks like we got 26 out of 52 total cards, right? So let's say we pulled out an ace of hearts. So this is gone right there. So when I go to pull out the next one, how many reds do I have left? 25. Out of how many cards do I have left? 51. That's the probability of pulling out. Again, this is dependent events. I'm kind of jumping ahead a little bit, but I think you can calculate that and see the difference, hopefully. This is a without replacement is a dependent event. So you go ahead and multiply those. That'll give you 650 out of 2652, or 25 out of 102, or 0.245. So about 24.5% probability of pulling a red card and another red card out. Right, here we got in Alex's drawer, she has 10 pairs of socks, looks like. Let me 6 are white, and let me do it this way. So she's got these 6 white socks, and there's 10 total socks, right? So the other ones are not white socks. Maybe I'll put socks, not white socks. Same drawer, she's got 7 t-shirts. So I'll do it this way. 7 t-shirts, or let me do white t-shirts. Oh, 3 of them, I'm sorry, 3 of them are white t-shirts. Oops, 3 are white. There's 7 total, so the other 4 are not white t-shirts. Okay, not white t-shirts. Now, she's randomly pulling out a pair of socks and then a t-shirt. That's kind of why I did it separately, because I know I'm pulling a sock out. I know it's the same drawer. I know I have to pull a sock out, and then I know I have to pull out a t-shirt. So are these independent events? Yes, because I'm guaranteeing that I'm pulling a sock out and then a t-shirt. It's almost like they're in separate drawers. Okay? Because I have to be pulling a sock and I have to be pulling a t-shirt, or it doesn't count. So independent events here. So probability of pulling out a white sock and then a white t-shirt would be probability of pulling out a white sock times probability of pulling out a white t-shirt. Well, the white sock, there's 6 of them out of how many socks? 10 total socks. So again, I'm guaranteeing I'm pulling out a sock. So I have a 6 in 10 chance of pulling out a sock. White t-shirt, well, there's 3 winning white t-shirts, and I'm guaranteed to pull from one of those 7 t-shirts, right? So 3 out of 7. And so you've got, 9 out of 35? Because that's 3 over 5, right? 9 out of 35. That's the probability of that occurring. Let's do some more here. A couple has 2 children. Find the probability of the children, both children are girls. Well, does the probability of the first child affect the probability of the second child? No, it doesn't. Either way, it's like flipping a coin, right? You got a 1 in 2 chance of having a boy or a girl. So these are independent events. So probability of having a girl and then having another girl would be independent events. Probability of the girl times probability of a girl. 1 in 2 times 1 in 2. So you got a 1 in 4 chance, right? If you think, you could also write that out, right? You could have a girl and then a boy. You could have a girl and a girl. You could have a boy and a boy, or you can have a boy and a girl, right? So you've got a 1 in 4 chance of having a girl and then a girl. All right, our last one before we move into conditional probability. You roll 2 die. Again, independent events, right? It doesn't matter what happens on the first roll. It has no impact on the second. So find the probability that the first die lands on an even and the second die lands on a 5. Probability that you get an even number and 5. So it'd be probability that you get an even number times probability you get a 5. Well, the probability you get you an even number, you have 3 winners out of 6. What's the probability you roll a 5? 1 out of 6. So it looks like we got 3 out of 36, or 1 out of 12 is our probability, right? You could probably visualize this too. Let's write it, all the outcomes out. I could roll a 1 with a 1, 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6. All right, so I wrote out all the outcomes. They should be separated by commas, but of rolling one die and rolling the other die, right? So I have 36 possible outcomes. But if you notice, I have to roll an even and a number 5. Here's my roll of rolling 5s on the second one. But I've got to roll an even as well at the beginning. So there's an even number 2 with a 5. There's an even number 4 with a 5. There's an even number 6 with a 5. So it looks like I have a 3 out of 36 possible ways to do that, or a 1 in 12. Of course, the formula would be, I think, a lot easier to do that, but you can visualize that. So that wraps up some examples of independent events where the outcome of event B or event A has no impact on the probability of event A occurring. Now, conditional probability, sometimes we need to compute the probability of an event given that another event has occurred. So insurance companies will use this to determine insurance rates, right? They'll do the conditional probability of you having an accident given variables like your age, your car, color, driving history, all this stuff, right? They'll base it on something, and then they'll say, well, this is what we're going to charge you because you're a high-risk teenager or whatever, right? So that's a conditional probability. The probability of event B given A has happened. That's probability of B given A is how that is read. Let's do some conditional probabilities, and then we'll get into dependent events with those, okay? So find the probability that a die rolled shows a 6 given that a flipped coin shows a head. Well, remember we talked about flipping a coin and rolling a die. Those are independent events, right? So what's the probability of rolling a 6? Well, it's 1 out of 6, because even though it's given that I flipped a heads, it has no impact. These are independent events. These are independent events. So either it's still 1 in 6. It has 0 impact on the probability of rolling a 6. So probability of rolling a 6, given you roll the heads, still 1 in 6. Independent events. Table below shows the number of survey subjects who have received or not received a speeding ticket and the color of the cars. Find the probability that a randomly chosen person, let's do part A, has a speeding ticket given. So what's the probability that we pull out of the bag somebody that has a speeding ticket given the fact that they're driving a red car? Given the fact that they're driving a red car. Well, if I see that I'm driving a red car, I'm only pulling out of the bag of people that have a red car. So how many red cars do we have? 150, right? There's a total of 150 red cars, it says on that far right. So what's the probability of pulling out somebody that has a speeding ticket, given they have a red car? Well, how many speeders that had red cars were there? 15. So I have a 15 and 150, in other words, a 1 in 10 or 10% chance of pulling out somebody that has a speeding ticket, given that they have a red car. Given that they have a red car. Now let's do part B. Part B says, what's the probability that you pull out somebody out of the bag that has a red car, given I'm only pulling out from those, pulling out those that have a speeding ticket. I'm only looking at those in a bag that have a speeding ticket. All speeders. I'm only pulling from speeders. Well, how many speeders do I have? 60. Good. I'm only pulling out of the bag of 60. What's the probability of pulling out somebody with a red car given they were a speeder? 15. So we got a 1 in 4 probability, or a 25% chance that we pull out a red car, somebody that has a red car, given that they have a speeding ticket. Right? So again, those are conditional probabilities. This would be a really good you try it problem, you guys. Similarly, conceptually, conditional probability. If you want to pause the video and work through it and check it. All right, probability that you're not pregnant given a positive test result. So I'm only looking at the positive test results. I'm only looking in that bag. In that bag, how many are possibly total outcomes? 75. There's 75 people that had a positive test, right? What's the probability I reach in of those 75 and pull out somebody that is not pregnant? 5 out of 75. So both those 5 divided by 5 is 1, 75 divided by 5, 15. So 1 out of 15, 0.06 repeated. Now let's do this next one. If you're checking yourself on part B, probability that you have a positive test given that you're not pregnant. By the way, this is called a false positive, right? I don't know how real this data really is that I pulled, but this is a false positive, right? I get a positive test, but actually I'm not pregnant. All right, so let's do that. Probability of a positive test given we are not pregnant. Here's all the people not pregnant. How many of them are there? 19 in my bag, right? There's 19 I'm pulling from. How many of those are a positive test? 5. 5 of those, 5 of those, were a positive test out of the 19. So 5 out of 19, or 0.263, so about 26.3%, have a false positive test result, right? All right, those conditional probabilities play into our dependent events. So we've talked about independent events. This is our official working with dependent events, even though we've actually done a few without replacement, right? But let's go ahead and do some dependent events. What's the probability that 2 cards drawn at random from a deck of playing cards will both be aces? So I got to pull out an ace and not replace it, right? So this is without replacement. So this is a dependent event. So the next time I pull an ace out, it's different. It has affected the probability the second time I pull, right? Again, dependent events. So dependent events, probability of A and B officially is probability of A times the probability of B given A, because given A affected it, right? So probability of pulling an ace and an ace would be probability of pulling an ace times probability of pulling an ace again, given that I already pulled an ace and I didn't replace it. And I did not replace it. So what's the probability of pulling an ace? Well, how many aces do I have? 4, right? I got 4 out of 52. So I pull it out. Let's say I pull out the ace of hearts. So that one's gone. Now how many aces? I'm trying to pull an ace out again. How many am I left with? But there's only how many cards left? 51. Yeah. So we're left with 12 out of 26, 52, which actually both of those go into 12. 1 out of, not very likely, is it, that I pull an ace and another ace out. So again, this is without replacement. That is different. If I had put the card back, that's an independent event. did not put the card back. That's why it's a dependent event here. Here's another one. This is without replacement. We're pulling 2 cards out. We want both of them to be spades. Both. So what's the probability? Spade and another spade. Well, if I'm pulling a spade out, I'm not replacing it, so it's affecting the second pull because I only have 51 cards left. So this is a dependent event. Probability of pulling a spade times probability of pulling a spade, given I already pulled a spade and did not replace it. So how many spades do we have? Good, 13. There's all the spades. 13 out of 52 is probability to pull a spade. All right, I pulled one out. Let's say we pulled out the queen of spades right there, gone. How many spades do we have left? 12 winners out of 51 cards left, right? We, again, did not replace it without replacement. And so this ends up being, oops. There's my 12, there's my 13, 52 is, so looks like it's 1 out of 17. That's the probability of that occurring, or 0.05, 8, 8, 2, 3, 5, 2, 9. So about 5.88% probability that occurs. And finally, let's go with a red king without replacement again. Without replacement, I'm pulling out a red king. I got to pull out another red king. Whoops, that's red king. So these are dependent events because the second pull is affected by the first pull. Probability of a red king and another red king. So probability of pulling a red king times probability of pulling a red king, given that I already did pull a red king. All right, so how many red kings are there? Let's see. Well, there's 4 kings, but only 2 of them are red. So there's 2. I have a 2 out of 52 probability of pulling a red king. Now let's say we pulled king of diamonds. So that one's out, right? I pulled that one already. Let's make it go away. So what's the probability of pulling another red king? How many are left? 1 winner is left. 1 red king is left, but I have 1 less card in there. I only have 51 cards left to choose from, right? And so we got, let's see, that would be 2 out of 52 is 1 out of 26 times 1 out of 51, so that ends up being 1 out of 1326, or 0.000754. So it's like a 0.08% chance. Not very likely you're going to pull 2 red kings on that. All right, so that's some conditional probabilities with involving dependent events. Thanks so much for taking notes. See you next time.